Math 1314, Tyler Junior College, Section 2.2, more on functions and their graphs, even and odd functions. In the previous video, we demonstrated test for symmetry for equations to determine if an equation's graph had x-axis, y-axis, or origin symmetry. But what if we don't have an equation but a function instead? Now, I could just say, well, the function really is an equation. We just have to replace the f of x with a y. So y equals, y equals, y equals, and then do the same test for symmetry. But for functions, we don't have to check all three, and here's the reason why. Of the three types of symmetry, y-axis, x-axis, and origin, one of them is almost always never a function, because one of them almost always fails the vertical line test. X-axis. That's a marker I need to throw away. Oh man, you can't see it, but the trash can's in the corner, little bitty space in the corner, and it went right behind the trash can. That's a shame. But a graph with x-axis symmetry will almost always fail the vertical line test because when you drop through it, it's on the top and on the bottom. In fact, there is only one function. There is only one function that has x-axis symmetry. I challenge you to find it. But in general, x-axis symmetry means you're not a function. So we only have to worry about y-axis symmetry and origin symmetry. And this will take us into the realm of what are called odd and even functions. So without further ado, a function is even if f of x equals f of negative x for each x in the domain. Let me translate that. A function is even if putting in a positive number gives the same answer as putting in a negative number. Putting in a positive number gives the same answer as putting in a negative number. Now, I know what the purists are saying out there. You can't say that. You don't know if x is positive or negative. So let me rephrase it. A function is even if evaluating it at a number gives the same answer as evaluating it at its opposite. In other words, evaluating in a positive gives the same result as evaluating in a negative. So for example, if a function's even, then I get the same answer whether I put in 3 or negative 3, or whether I put in negative 8 or 8. Even functions will give the same answer in those cases. A function is odd if f of x equals negative f of negative x, so negative on the outside and inside, for each x in the domain. Translation. A function is odd if putting in a negative gives the opposite. Excuse me, let's try that again. A function is odd if putting in a positive gives the opposite of putting in a negative for each x in the domain. And for the purist, a function is odd if putting in one input gives the opposite value of putting in the opposite input. So another way of thinking about it is even means opposite inputs produce equal outputs. Odd is opposite inputs produce opposite outputs. I think that one is worth writing. Even. Equal inputs implies, not equal, opposite inputs. So the same numbers, except one is positive, one is negative, implies equal outputs. Where an odd function, opposite inputs, implies opposite outputs. Now it's worth mentioning that functions don't have to be even or odd. You can put in an opposite input and get two completely different answers like 5 and 19. But if opposite inputs like negative 3 and 3 both turn into the same number like 9, or opposite inputs like negative 2 and 2 produce opposite outputs like negative 8 and 8, that's what constitutes being even or odd. All right, so let's analyze these functions to see if they're even or odd, and then I'll tell you what the heck this has to do with symmetry. It's actually pretty easy using the definitions I've given you. And just to warn you, some textbooks give a slightly different definition for odd, or they have the negative over here instead of there. I like having the negative over, which by the way is acceptable because I just multiplied both sides of the equation by -1. If I multiply both sides of this equation by -1, it puts the negative back over there. But I kind of prefer this definition because it's asking you, does something equal the original? This one says, does f of x equal the original? This one says, does negative f of x equals the original? So there's a natural sequence in which to check these. Calculate f of x and see if it matches. Then take its opposite and see if it matches. So let's see what happens. For f of x equals x to the 4th minus 5x to the 5th, we first start by calculating f of negative x to see if these match and say that it's even. F of negative x means that I replace each x with a negative x. So I will have in parentheses negative x raised to the 4th power minus 5 times, in parentheses, negative x raised to the 2nd power. It's been a long day. What do even powers do to negatives? They turn them positive. Here's 4 negatives. They all pair off and become positive. So this negative disappears, and we're left with x to the 4th minus 5, and the same thing here. This even power turns that negative positive, so it's gone, but this one is still there. So the negative x squared becomes an x squared, and if you'll notice, this is the original function. Since evaluating the function at a negative is the same as evaluating it as a positive, that means that f of x is even. I don't know if you've seen the symbol before, the 3-dot triangle. It's a symbol for the word therefore, mathematically. It means we're about to draw a conclusion. Therefore, f of x is even. There is no need to check if it's odd, and here's why. If it's even, stop. If it's even, it means these match. To see if it's odd, we'd have to take the opposite of that, and it's not going to match anymore if we take its opposite. But if you just wanted to check, negative f of negative x is the opposite of what we just found. We just found x to the 4th minus 5x squared. And what's the opposite of that? Distribute the negative. Get negative x to the 4th plus 5x squared. This is not equal to the original. So the conclusion that we draw here is that f of x is not odd. Not odd. That says not. I promise it does. There we go. So check even. If it is, stop. If it's not, take the opposite and see if it matches. All right, so let's try g of x. G of x equals x over x squared plus 1. This is called a rational function. It's a ratio of polynomials. First, we need to check if the original function is equal to g of negative x. So if we evaluate g of negative x, we need to replace each x with a negative x. On the top, I really don't need parentheses. It's just an x. I'm going to take it out and replace it with a negative x. But on the bottom, I do need parentheses because the x had a square on it, followed by a plus 1. So if we put a negative x in the denominator, and the parentheses in the denominator, then g of negative x is equal to negative x on top, and on the denominator, the square cancels the negative, and we're left with x squared plus 1. Is this the original? Almost. The denominators match, but not the numerators. So this is not equal to f of x, and the conclusion we draw there is that, I'm sorry, it's not f of x, it's g of x. So the conclusion that we draw is g of x is not even. But we're not done, because now we have to compare to the negative of g of negative x. And if you're freaking out because these say g's and these say f's, I've mentioned before that the name of a function is arbitrary, so whether it says f of x, g of x, or beta of x, if you want to use Greek letters, is completely irrelevant. So we need to find negative g of negative x. That just means stick a negative on the answer that we just found. So let's stick a negative in front of this fraction. negative of negative x over x squared plus 1. Here's a little story about negatives and fractions. They can go in 3 places: in front, on the top, or on the bottom. Guess where I'm going to put this negative? On top. Why? Because if I put it on top, negative times negative makes positive. So the top becomes a positive x, the bottom is x squared plus 1. Is this the original? It is. This equals the original function. And since the original function is equal to the negative of g of negative x, the conclusion is that g of x is odd. Let's try the last one. This function's kind of simple. It's not going to take too long. H of x equals 7x plus 4. First, we have to evaluate h of negative x to see if the function is even. This is pretty quick. We get 7 times negative x plus 4. 7 times negative x is negative 7x. So h of negative x is equal to negative 7x plus 4. Is this the original? It is not. It almost is. It's off by a negative sign. So the conclusion here, it's not an even function. But we also have to compare it to the opposite of h of negative x. So we just have to stick a negative in front of the entire result that we just got. So the negative of negative 7x plus 4. If we distribute the negative, that will turn the 7x positive, which is what was wrong in the previous one. However, when I distribute the negative, it will turn the 4 negative. And this is still not equal to the original function. So this means that the function is not odd. So it's possible to be even, it's possible to be odd, but as a function, it's not possible to be both. Well, there is one function that is both odd and even. It's also the same function that has x-axis symmetry. I challenge you to find it. Oh, I forgot something important. I'm going to start another video. Now, I can say what I'm about to say in 60 seconds. So what's the big deal with even and odd? And what about symmetries? Here's what you need to know without examples to demonstrate. Even functions have y-axis symmetry. So that's statement number 1. And statement number 2, odd functions have not x-axis symmetry, origin symmetry. If you think about how you can change a function back to an equation by replacing f of x with y, then you can see why an even function would have y-axis symmetry and an odd function would have origin symmetry. Or, if your x's are opposite, you have the same y value, so you have mirror images across the y-axis for an even function. But if you're an odd function, opposite x's have opposite x values, so you have that rotational symmetry, I feel like a teapot, and therefore odd functions have origin symmetry. See, told you it wouldn't take that long.